So far in the course, we've been studying the motion of collections of particles. We would now like to consider rigid bodies. Now, rigid bodies can be translated in space as I move it like this, or we can rotate this rigid body about some point. I can rotate it about the end point. I can rotate it about a point which we call the center of mass. So I can rotate it about the center of mass. I can take the rigid body and I can rotate it about the center of mass and also translate it in space. So there's many types of motions that we can do with rigid bodies. Sometimes the motions are quite complicated. If I spin it like that, it is a very more complicated motion. You can see that it's rotating about this axis. So what we'd like to do now is analyze how to think about the motion of rigid bodies. And what we'd like to do is idealize our rigid body. So let's just draw, even though we looked at a rod here, let's just draw some extended idealized rigid body. And let's identify 2 points in that rigid body, the jth point and the kth point. And we'll think of our rigid body as a bunch of point-like particles, mj and mk. And the important thing that defines a rigid body is the condition that the distance, and we'll draw this a vector from the kth particle to the jth particle. So we'll draw that as r, j, k. And actually, I would like to write it from the kth particle to the jth particle, r, k, j. And our condition is that the magnitude of this vector, which I'll denote as rkj, is constant for all points j and k. Now, what does that mean? That means the distance between any 2 points in the rigid body stays fixed, no matter how the rigid body is moving, and no matter what 2 points I choose, the distance between any 2 points is fixed. So we'll rewrite this as the distance between any 2 points is fixed. So that doesn't change. And that's what we call the rigid body condition.